Welcome, everybody. My name is Stephen Holes. I'm the Assistant Project Manager for the University Innovation Project, and thank you for joining us today for another ULI Tech Talk. For those who are unaware of what the ULI program is, the ULI program is the University Leadership Initiative program under NASA Aeronautics, provides the opportunity for university teams to exercise technical and organizational leadership in proposing unique technical challenges in aeronautics and developing multidisciplinary solutions. Before we get into our tech talk today, putting a few things in the chat. If you would like more information on the ULI program, please see the chat. There will be a link. Also, to view previous tech talks, there is a page where this recording will be posted eventually, where you can view all of our tech talks that we have. If you would like to be put on future invites for ULI tech talks, please see the sign up form if you're internal to NASA, or email me indicating your interest if you are external to NASA. And if you have any questions during the presentation today, please type them in the chat, and we'll call on your questions during the Q&A portion after the presentation. Now I'm going to hand it off to the PI for the project, Dr. Topku, to go ahead and kick off our ULI Tech Talk. Thank you.
Thank you, Steve. Okay, so I am Ufuk Topku from University of Texas, and I will present with Hamza Balakrishnan and John Paul Clark, who are also PIs in the project. And I will tell you who else is in the team later. So we are about to come to the end of the second year. That's the timing of things. The team is, in addition to Hamza and John Paul Clark, we have Karen Wilcox from University of Texas. University of Texas is the lead institution. From Purdue, we have Karen Marai, Danfeng Sun, and from MIT Lincoln Lab, we have Matt Edwards and Allison Chang. From Morgan State University, we have Billy Rockwood, and Caravan Solutions, Stephen Brett Stroop is the PI from there. And of course, this is just the tip of the iceberg. We have so many other people contributing to this project, all the way from undergrads to senior researchers at several participating institutions. All right, with that introduction, the objective of this project is, in the more visible text there, is to establish a foundation that will support the development, deployment, and adoption of advanced air mobility systems for autonomous cargo operations at scale. The at scale part is we were addressing the scaling up operations priority area or thrust area in the plans. And the foundation is going to include algorithms and theory behind these algorithms. But in addition to that, we take a close look into concepts of operations that may motivate the effort, that may help us focus on more pressing issues. And it is not only a vehicle, or it is not only a traffic management problem, but we want to look into the spectrum of challenges, including vehicles, traffic, and also fleet operations. And there's going to be a reason for that. And we debated quite a bit whether we should actually narrow the scope of the airspace that we look into, but then we realized that one of the bigger challenges is actually this interaction between different airspaces. And we said, for now, let's actually keep all airspaces within scope, and as we go along and as we learn, we will probably prioritize some of those things. And here's a little bit of an overview of the project. We have 3 chunks, or just thrusts. The first one is verifiable safety, and the main question that it is trying to address is how can we scalably verify system level safety properties and identify appropriate requirements. And we believe that through the impact of the work that we do in this chunk would be trying to predict the potential risks that we would take due to weaknesses of regulation. And if it is too restrictive, that may also hinder the potential innovation. So we want to inform that kind of decisions here. The middle point is whether the technology is ever going to be adopted by the public, and this is of course an extremely broad question. And we wanted to look into how we can constrain the design and operation to account for a few things that public might actually be more receptive to. And we identified noise footprint, the infrastructure, the visual footprint of the infrastructure that, for example, we have to put up for communication, and the risk and privacy perception of the public. And then the last piece is whether it is going to take investment, right? Just be able to realize the vision of advanced air mobility in any version of it is going to require infrastructure investments. And the question is whether this is going to be economically justified. So how can we optimize the operation of air mobility systems at all relevant scales, and whether we can scale up the economical impact to match the investments that we would have to make. And this is not within the direct scope of the project, but we thought that whatever we do in these three chunks would have to be compatible with the underlying infrastructure and compliant with the regulations that we have. And we see it actually a two-way interaction, not only be compatible with the infrastructure, but inform the infrastructure decisions that we would have to make and inform the regulatory decisions that we would have to make. Regulation and infrastructure is going to be a very central element of this entire enterprise. On the other hand, both of them are just in the making. So we thought that this would be a great time to try to see if we could take to some extent a clean slate perspective, whether we can inform these kinds of decisions. And of course, this entire thing sits on top of the education and outreach plans that we have. And we will have a slide at the end on that. At the time of the proposal, we were actually very excited to see that there are lots of industry partners and other stakeholders who found this idea interesting, and we had a good number of letters of support. To a very pleasant surprise is that multiple of these stakeholders have stayed engaged. They have been coming to our meetings, review meetings. And also along the way, we have been able to identify additional partners. So that's very exciting, and it shows that this is a very happening domain. I will not have time to discuss the ConOps development that work that we have been running, but this has been a very integral element of the project, mainly spearheaded by our partners at MIT Lincoln Lab and Common Solutions, and we have been focusing on Dallas-Fort Worth area because there's quite a bit of interest in that area, and then also some different but complementing aspects from a few use cases in the area of West Virginia, and we ran a roundtable last year in West Virginia at Marshall University and try to identify what aspects we should try to include in our ConOps. And this event and the conversations around that have actually been influential in our prioritization of the ConOps. What we thought would be interesting when we could reach out to the local stakeholders, a good number of aspects that we were excited about were, after all, not that relevant. And through this interaction, we identified other relevant aspects of the potential impacts of advanced air mobility in that area. So there's a working document. If anybody is interested, we can share and we can discuss. But with that little comment, we'll just go into the three thrusts or technical challenges that we had in our proposal, or as well as in our project. The first one is whether things are going to be verifiably safe. As the naming suggests, that this is how we can apply or develop new verification methods in the context of problems that appear in advanced air mobility. So I will do this part. Second part will be done by J.P. Clark, and the third part is going to be done by Hamsa Balakrishnan. So the first technical challenge, we thought that we would take a compositional and hierarchical view on verification because of the scope of the operations. And not every layer is relevant directly, but here is a problem that we look into, which is traffic management or volume management. Each of these circles is an area, and each of these areas that may include some vertiports, or at the time the buzzword was aerodrome, and they manage the traffic around them. And then at intersections, overlapping areas, there's going to be a handoff of vehicles traversing through these areas, there's going to be handoff from a vertiport to the another vertiport for the vehicle to report to. And we want to be able to formulate control and deconfliction and strategic and tactical reasoning problems in a setting of this sort. And the hierarchical reasoning is going to obviously try to decompose the problem into different views of the overall problem, solve each bit of each layer, and try to ensure that whatever we do in each layer is going to be consistent across the layers, so that when we put them together, we will have a complete problem, sorry, complete solution that we can argue to respect the overall requirements we have on the system. So to that end, as I said, we try to take a compositional view, and here's a problem, a representative problem that we have been studying. This is mostly dynamic airspace management. On the left, I have a more limited view of the setting that I showed, and the overall system is to satisfy the conjunction of building blocks of some specifications, and some representative specifications are here expressed in temporal logic. That is not that critical, but a formal specification language, why not temporal logic there? And we can debate whether it is expressive enough, but for now it will do the job. And the objective is these circles are compositions of things. This big parentheses corresponds to a big circle here, and there is going to be a decision-making algorithm for each of these regions. It is called aerodrome hub. A couple of vertiports are managed together, somehow coordinated. And in addition to that decision-making logic for the area, these S's correspond to each black dots, which correspond to the vertiports themselves. So for each vertiport, we have a decision-making logic, and then they are composed, and the entire thing is composed for the decision-making logic for that area. And then for each area, we have the same thing, and just this overall composition, we are interested in whether they will satisfy the specifications or not. And we are trying to distribute the synthesis and actually execution of underlying controllers or decision-making logic for this. And for that, we try to develop, we try to decompose the problem using a contract-based reasoning. So now going narrower and narrower, this picture here focuses on the interactions between two hubs, two regions. And then this figure on the right-hand side is looking into now only a single area. And obviously there is a need for coordination between the vertiports within the area. So each vertiport has its own requirements, the guarantees that it is trying to satisfy with respect to the rest of the world. It is saying, hey, I will satisfy these things as long as the assumptions are valid. It makes assumptions about the world, and as long as those assumptions hold, I guarantee you that I will do the same. I will satisfy my requirements. And of course, the question is between each of these actors, between the vertiports and vertiport regions, how we can come up with these assumptions and guarantees in a consistent manner. Each of them locally satisfy their guarantees as long as the assumptions hold, and then we can propagate to a guarantee at the system level. So it is the name of the game here, how we can come up with each of these assumptions and guarantees for each of the elements of the problem, so that consistently the composition yields what we asked them to do. And we had done a little bit of work on that, and there is going to be multiple levels of the views, how these resulting protocols will be implemented. There's going to be a version of that at the vehicle level. There's going to be a version of that says system level implementation, but even that has layers. Each vertiport will have its own implementation, interpretation of the resulting logic and implementation of that in its interactions with the other vertiports. And even the vertiport region or the hub is going to have its own interpretation and implement that, and we'll try to keep all those things in sync. This little thing is here a in-house simulation, but I'm just going to go actually to a little bit more interesting simulation that we have been looking into how we can implement these things in high fidelity simulators, which is in this case Blue Sky. And each underlying system here, each vehicle here implements some strategy for collision avoidance or separation assurance that comes from some learning algorithm. In this case, it's some reinforcement learning algorithm where the policy is represented as a deep neural network. And the region is here, the northeastern part of the FW region. Over the entire execution, we will see 180 vehicles entering, and this is going to be an execution over 1 hour and 30 minutes. And this is actually a part of the collaboration we have with a system-wide safety project, and the students from the UT Austin were contributing to both sides. That's why I actually picked this. And the setting is this region is going to be looked into as a network. Each of these intersections, these correspond to intersections. There are two-way pathways between them, and they are, in this case, they are actually these bidirectional routes are borrowed from the helicopter route charts published by FAA instead of trying to invent something new. So that gives a sort of a discretization of the underlying workspace that we have here. And then if you look at closer, intersections will be managed by some control logic. The vehicles may send requests as they approach the intersections. Those requests may or may not be accepted. They may be denied. If it is denied, the vehicle needs to find a way to actually spend time and not enter the region, or it might make its own decision and try to go in a different direction. But if it is denied, it cannot enter this intersection. And if the request is approved, then obviously it can traverse through the area. And then these text and boxes here should give a little bit more details on how we model the setting. And then also the entire system operation is going to be subject to some assumptions that we can make, reasonable assumptions that we can make about the system and the environment in which we're operating. And each of them have their own requirements. For example, the system is going to operate under the assumption that the number of approvals will never exceed the number of requests. Obviously, that would not make any sense. And then the requirements may be approvals shall not result in a violation of the maximum capacity constraint. This is a requirement that we put on the strategy synthesis. So we want to synthesize a strategy that, when is implemented in this environment I showed with the modeling assumptions that we make, is going to run the entire system in such a way that we will never approve entrance of vehicles at a higher number than the maximum capacity that we have. I'm not going to read the rest, but this is just as it goes, how it goes. We might have prioritizations and other things. So we implemented the procedure that I mentioned and demonstrated this thing on the Blue Sky and high fidelity simulation environment that I mentioned. We also recently, we had, right before our second year annual review, led by MIT Lincoln Lab and a few others contributed, we had this demonstration. You cannot see it, but this is a setting where we have two actual vehicles and two or a few simulated vehicles creating traffic around them. And we try to demonstrate this, some of these algorithms on actual hardware. And I would say that this actually went pretty well. So this vehicle is here waiting, I think, for this vehicle to go in its, just get away from it. And we don't see it, but there's simulated traffic as well. And this was fun to watch. There's a little bit too much noise right now. I'm not going to play it, but it was fun to watch with the soundtrack in the background explaining what vehicles are coming and which vehicles are reacting to what. To be able to satisfy specifications on the traffic flow. So I will skip I have two other examples of the type of work that we do in this project. One of them is trying to understand if pieces of the models that we use come from a learning element, from a data-driven modeling framework. We try to capture the resulting systems as parametric Markov decision processes and try to understand changes in which parameters would have higher impact on the system execution. And we try to use this modeling and sensitivity analysis framework as a tool for dynamic certification or verification of system behavior throughout the lifetime of the system as requirements and our understanding of the system actually evolve. If there are any questions, we can get to that, and I will skip this piece. And I want to just say that the project has enabled us to interact with other projects or other events that are happening with NASA. One of the recent outcomes is this autonomy verification and validation roadmap and vision for NASA 2045. And we have been lucky to participate in this and reflect on some of the outcomes of the project that we had into the autonomy roadmap document. With that, I'm gonna end the discussion for the technical challenge 1, and technical challenge 2 is gonna go for, and JP Clark is gonna speak to that.
Hi, greetings everyone. So folks, I'm going to talk about our second technical challenge, and the questions we're really trying to answer here are the illities. You know, how does the acoustics, the privacy, the risk, the things that people on the ground while you operate air vehicles around care about and are sensitive to it. So the questions is, how can we adopt it? Will it be adopted by the public, or at least accepted by the public? Does it align with the public's interests in terms of their sensitivities to issues? Next slide, please. So the overarching idea for this particular thread or thrust or TC2 is that we want to bring all the illities or all the issues or the concerns or constraints to a common basis. And, you know, typically we try to do that in terms of cost, but the idea here is that we're going to basically match it up with terrain. So if you think about it, all those illities are addressed by keeping vehicles either closer to or further from something. So we have a physical terrain that we definitely don't want to fly into. And if we can convert the noise constraints, the safety constraints, the privacy and the perceived risks into the equivalent of terrain, then we can take what could be a complicated, and it's often a complicated optimization problem, nonlinear optimization problem, to basically a terrain avoidance problem. And so that's the underlying idea, which is to support trajectory planning and optimization with basically converting them to terrains. Next slide, please, Ufo. So give you an example of the challenges here. You know, suppose we were trying to figure out what's the best way to route some eVTOLs or AAM over a cityscape. And you'd have to basically then create trajectories, run the trajectories, do a simulation of the trajectories, the aircraft thrust, and the noise source characteristics of propagation, including all the reflections, the obstacle, basically blockages by buildings and other obstacles. And then for each path, you'd get a noise signature, and it's typically we refer to as a noise contour, but this is really a reflection of what the noise values are on the ground or at specific locations. And then we'd have to iterate. Okay, what if we change this? And it would be a very complex nonlinear optimization problem, which is computationally expensive. So the idea, next slide please, Ufo, that we have been deploying is an idea that's been on our minds for a long while, which is rather than having an iterative loop, which you can see at the bottom left, where you go, for example, in acoustics, you do a trajectory, is it feasible? You know, what is the noise? You do some changes and you constantly going back around. What if we basically said, okay, let's create a equivalent of a physical terrain. And then basically what we then do, and we also have with the noise, and that's on the right-hand side. And now you have basically two sets of terrain, the physical one and the noise terrain. And then you basically say, okay, am I above both terrains? So you take basically the combination of the hull around both of those terrains. And how do we do this? Next slide, please. would be using the principle of acoustic reciprocity. And we have reciprocity in everything we do, right? I mean, we have the one that we're most familiar with is when somebody is taking a picture of a group, a large group, and they say, if you can see me, I can see you, right? That's basically a visual reciprocity. Well, the same holds true for acoustics. If I have a source at one location and a receiver at another location, and I switch their positions, the noise that you record at the receiver is going to be the same in both scenarios. We have electrical reciprocity, we have mechanical reciprocity. It's a very common phenomenon in nature. So the idea is rather than basically taking the aircraft and saying, here's where the aircraft is going to be, what I'm going to do is say, I want to put the aircraft where my receiver is, down on the street level, at the height that people would hear, generate noise at the same source level that it would be when it was flying, and then do ray tracing in the opposite direction, basically in a reciprocal direction, hence the principle of reciprocity. And that would give me, and you can then basically plot a surface where the noise level drops to the acceptable level. So typically 60 dBA is a conversation between two humans. Casual, not a heated conversation, it's a regular conversation. And so if you had a source that was, say, 120 decibels, you put it on the ground, you'd propagate it backwards, and then you'd create, as you can see the top right, a surface that would be at joining all the points that were at 60 dBA, and that would become your terrain. And so the bottom row here of this slide, you see for the same source, if you have 65 dB is your contour, and it's a slightly louder, obviously the hill would be smaller because you can get closer to the location that you're concerned about. If it was 60 dB, it would be a little bit, larger terrain. And if it was 55 dB, it would be even higher terrain. So what this allows us to do is then take noise, turn it into terrain, and we can basically set a source noise level for the vehicles that we consider. And we would then also basically set the noise level of concern, and we'll have a terrain. Next slide, please. And so we can do the same thing with safety risk. We can actually say, okay, given a vehicle that's flying, and this probability that it's going to, some failure will occur, and the probability, a conditional probability that you can actually do a recovery maneuver, and the likely recovery maneuver, and when it hits a building, how good the building is in terms of fungibility, and all of these different safety issues, you can then basically say, and you look at the traffic level below, for example, and the probability that you'll basically hit a random person walking along the street or a random car driving along the street, you can come up with basically equivalent risk surfaces. And you can see here on the top, you'll see basically you want to be at 10 to the minus 8 risk level and a failure rate of 10 to the minus 5 per flight hour. And you can see here at 12 p.m., it will be different from 5 p.m. versus 10 p.m. because obviously the amount of folks on the street or the people that are driving will be less or more. And then we can also combine the two together. And this is, as I said before, you have the on the bottom left, the virtual acoustic terrain, in the middle, the virtual risk terrain, and then you can combine both of them. And basically you satisfy both your risk and your noise constraints. And next slide, please. And then further, we can go to privacy and basically look and say, where people have line of sight, where do people, worry about somebody flying over their backyard while they're doing a barbecue, and they don't want anybody to see what they're doing in their backyard, or through their window. We can create the equivalent there, and this is just basically line of sight, reciprocity, and you can come up with basically privacy surfaces. This one is a 2D one, which is just basically from above, but you can get more complicated ones as you go on along. And so, next slide. So let me just go a little bit into the noise one and in a little bit more detail, now you have the flavor. And so what we have is the next slide at the tool chain that we've built. And so we have a complete tool chain which uses data, publicly available data, as well as easily accessible tools. I'm not saying inexpensive, but or free, but not too expensive tools and popularly used tools to basically capture the urban environment. So, for example, the figures I showed you before or for Chicago, the loop, and I'll talk about that in a second in more detail. And then you can basically go through and simulate all the noise propagations, including, I saw that question that popped up, the resonances and the constructive and destructive. If you do it on a third octave band basis, you can include all of those. And then you can then go to, the data extraction and post-processing with visualization. So next slide. And so this is the example of the Chicago loop model I mentioned. We were able to get a very good quality 3D model. Together, receiver grid together, and then we basically put the source noise on the ground. Sorry, you went to the next slide. And then the source noise on the ground, and then basically, and then look at the impact of the buildings, and you can see the reflections off the buildings, the blockages, the shadow zones, all of that captured there. Next slide, please. And then this is for a numerical setup that we did. We had basically looked at one frequency here, just for here. We looked at 100 dB noise source, monopole directional activity. Look at the number of sound particles per source, the 100,000. So you can see here all the different parameters that you might expect. Looked at this is on details, and we have a paper we can share about this for those who are interested. Next slide. And then here you can see again, going back to the model, you have the 60 dB. You can see all there. This is the model. This is at 70 dB. You can see, if you're only worried about noise above 70 dB, then you can pretty much fly anywhere. If you really want it quiet, down to 50 dB, you basically have to stay above all the buildings and well above all the buildings. If you think about 60 dB on the bottom left, then you can see where you could potentially put your vertiport. So this is also very useful, not only in terms of where you want to fly, but also where you should put your vertiports, which buildings, etc. makes sense for those. Next slide. And so just to summarize, the key concept, reciprocity. We're basically taking all the considerations, the illities, the societal concerns, turn them into equivalent of terrain, and then combining them with the physical terrain to make basically to give folks who are doing the trajectory planning problem a basically defined no-fly zone that you can basically stay above that. And we also have in this project, which I didn't mention, we actually are also looking at the communication and navigation capabilities, GPS availability, as well as the availability of 5G and 6G for comms and nav. And that will define a go-fly zone, or a zone you should be in. And so between those two, we'll have a feasible operating range for which you can optimize the trajectory. Thanks. And that's me, I think, correct?
Yeah, I think next is Hamza now.
Thanks, Ufuk, and thank you everybody for joining us today. So I'm going to be talking about the third and the last of the technical challenges. And this one focuses more on the optimization at the various scales that we've talked about. And as you'll see as we go along, a lot of it is taking the constraints and the considerations that are popping up from TC1 and TC2, and then bringing them into the actual, how would we optimize operations at different scales that that satisfy all of this. And a relevant part of it that we're also interested in is really the economic piece, which is what kind of business models could we actually have to make these things, the sort of autonomous cargo operations work. Next slide, Ufuk. So as I said, we're going to be dealing with optimization models. I should also mention that this piece, I'm going to be talking about it, but it's work that's being done by MIT campus, MIT Lincoln Lab, and also Purdue. Increasingly, as the project matures with input from all the groups, since we're actually taking things from TC1 and TC2 as well. So in terms of the models themselves, I said there are different scales, but there's also different temporal scales that we can think about, and we do think about. So at a sort of long-term level, there are issues around infrastructure planning. So there isn't an infrastructure for autonomous air cargo operations at this point. So there are questions of how do you design the network? How do you understand what the fleet should look like, and then allocate the fleet to different routes, and then even for the corridor design. So which vertiports do you connect, or aerodromes, as Ufuk said. And so the structure of the network and the fleet allocation pieces, which would happen at longer time scales. And then the more tactical piece, which deals with planning and execution, and there are optimization problems around these as well. So not the fleet allocation, but the more fine-grained vehicle assignment, including which packages go on which vehicles, the routing piece, which is very operational and very important, and there are lots of optimization problems there that I'll talk about a little bit. The scheduling piece, and then the maintenance scheduling, the congestion management, and ultimately, since we're also interested in the economic pieces, how the revenue models work and how profits work in these operations. Next slide, Ufuk. The use cases are, and I wanted to talk a little bit about this because this also leads into the ConOps development that Ufuk mentioned. When we set about, and we've been refining this, we see three broad use cases that we would be looking at when we're thinking about optimization. The first one really is at a policy side with the FAA or any other policy maker here. So what would you want, if you want to have autonomous cargo operations at scale? Some part of it is, what is the policy that can actually stimulate the demand, or enable the operations that you might want to, there might be demand for at a large scale. So the optimization opportunities we see here are more at the infrastructure planning and the strategic level. So network design issues, especially where do you put your infrastructure, the corridor design, but also congestion management, which would be the equivalent of traffic management that the FAA does now for conventional aircraft, and then the economic policies that play a role here as well. In the next time scale, we also see interregional, so medium haul to longer haul operations currently, as we would refer to them. And as Ufuk mentioned again in the ConOps development, a lot of it we were looking at were sort of Dallas-Fort Worth and West Virginia. We found that through conversations that there are certainly areas of need here where we could be using that to inform our concept of operations. And so here, it would go to the next level, the next time scale to some extent, which is not the policy, but really the fleet allocation, the vehicle assignment type things for these medium to long haul operations. And then again, warehousing and then transferring between transshipment issues here as well. And then there is at the last mile scale, we look at delivery, and we say food delivery here in that picture, but really we're looking more at any form of cargo delivery that you could be looking at. And in the use cases that we were looking at with West Virginia, especially, there are lots of first responder type things or essential supplies that we are interested in looking at here. And in particular, the optimization opportunities that we see there are looking at the constraints on safety or privacy or noise that the TC1 and TC2 identify, and incorporating them into the optimization formulations. Next slide, Ufuk. So in terms of the larger scale network design operation, what the challenge here really is the multiple spatial and temporal timescales, and in particular, what does the infrastructure here look like, where you have different cost models, and you have different types of capacities in your vehicles, and you need to scale this to a large number of aircraft. And so the kind of outputs of the optimization that we would want to see is for different potential cost models or difference in cost between aircraft types and aircraft sizes, and with the turn times that are afforded now by autonomous operations, what would your networks look like, and where would you put your hubs? And that's really one part that we're trying to understand a lot in this process, which is where do you put your vertiports, and where do you put your vertiports with the facilities that are needed to actually do a lot of transfer cargo in order to have the most resilience. So Ufuk, could you go to the next slide, please? And so some part of this for us is problems of hub selection, vertiport selection, fleet sizing, and the routing between the vertiports. There's the optimization piece that we've been working on. And then more currently, what we're working on is also trying to understand current air freight demand and freight demand in general to estimate what the potential for autonomous air cargo demand would be, and also try to understand what are the things we could optimize, but we also need to know the objective function for the optimization. So what are the things about current hubs that make them good hubs? How do we identify good network structures for freight operations, especially when it comes to characteristics that we need to also include in autonomous operations? And so a lot of more network theory-based analysis that we've been working on here. Next slide. The second piece, because we're interested in operator utilities, is both trying to elicit. So, how do you even model utility functions and cost functions for different fleet operators? And then the many trade-offs that are going to exist between efficiency, fairness, resilience, and economic fairness and operational efficiency as well. So if you go to the next slide, this is just an example of one piece of work here where when we think about congestion management, actually looking at things that also include these economic issues or considerations, and coming up with protocols for traffic management, congestion management that also look at different flight costs. So there's the optimization or the allocation piece of the airspace, but then taking into account different costs, that the aircraft or the flights are heterogeneous, and the operator models might be business models might be different. And so here, coming up with trade-offs between the economic efficiency and the operational efficiency, or fairness and operational efficiency. And so in the plot, this is an example of the kind of things that we look at, where you want solutions that are both fair and efficient, both economically and operationally. And so coming up with methods, traffic management methods, which include layering pricing mechanisms on optimization to get to something that's both fair and efficient. So next slide. So I'm going to go through this very quickly. The other piece, if you can build this through, is routing with privacy. And we're not looking at the privacy on the ground like what JP was talking about in TC2, but we believe that with remote ID, there's also another issue, which is the privacy to both the customers who are buying it and buying the goods and the vendors themselves. And I should mention, I did see Max Lee from Michigan, who's here, and he's been very closely involved in this work as well. So if you go to the next slide, the issue here built through is that with remote ID, if you're actually broadcasting information, then it's possible to map customer to vendor. And what we would like to do, if you go to the next slide, is skip through this. I think I'm very mindful of time, is if you have, 3 vendors, if you go to the next slide, and build through. So let's suppose you have 3 vendors and 3 customers, and there's a drone that's taking a particular route with, between vendors to customers. And what it's doing, it's delivering the apple to the last customer to A1, V1 to the apple to A1, the ball to A2, and the pen to A3. How can you do this in a way where somebody who's actually watching the drone and the route a third-party observer cannot infer who is delivering to whom? Because there may be situations, especially if these are, certain medication or, expensive products, where you don't want, either for competitive reasons or for privacy reasons, to do this mapping. So if you go to the next slide, Ufuk. The piece that we deal with here. So the first piece is just mathematically, how do you define privacy risk? Namely, the probability that you can actually, map the vendor to the customer. And if you go to the next slide, the second piece is optimizing over this. And so building models or optimization methods that can actually use vehicle routing problems and incorporate these privacy concerns into vehicle routing problems. If you go to the next slide, Ufuk. And there are a set of challenges here in being able to do this because you don't actually, there are too many combinations, and so it's going to be really hard to do it. And so we come up with some nice methods to do it in a tractable way that we can actually incorporate this. So if you can go to the next slide. And so this is just saying that, which is we can use this idea of what we call route families to come up with ways in which we can do this mapping. So next slide. And we run this to a couple of case studies. And so, comparing some heuristics as well as the most efficient solution and the most private solution. And so I'm just going to talk about one example. Next slide. Where if you have, build this through too. So if you have two clusters, so all of the vendors are on one side of the river here, and all of the customers are on the other side. Ufuk, could you click through? Thank you. What you can find is what the trade-offs here exist. Namely, if you increase the capacity of your vehicles, you can take more packages, and so it's harder to tell who got what, and so you get more privacy with more higher capacity vehicles because you're doing the aggregation. You can improve efficiency because you're doing fewer back and forth trips with higher capacity. And then if you click through once more, you can actually improve capacity in this case, privacy in this case, but there's a trade-off in the case of in terms of efficiency. If you go to the next slide, we can do the same thing. I'm not going to go through this example, but we can do the same thing with hub and spoke models as well to say, okay, what are the trade-offs here? So to sort of wrap up, if we go to the last one, what we have now is this method, and we're trying to incorporate, various nuances into this. And then also we've been, as part of this project, been doing a discrete choice experiment where actually surveying people on how much, consumers actually trade off value privacy and trade off the cost versus privacy. And the short answer is it really depends on what you're getting delivered, right? There are things where I don't care, and there are things that I do care, and that makes sense. But we're trying to infer this. So to wrap up on the last slide, if you go, what we're doing is incorporating now more and more of the issues that we've identified. The piece that I didn't talk about that Purdue Dengfeng's group in particular has been working a lot on is really last mile aerial routing and potential fields. So coming up with a large database in the, covering the geography of the US that's looking at these potential fields on the ground that we're excited that going forward we'll be able to use to actually do more of the optimization. So with that, I'm going to hand it back to Ufuk to talk about the education and outreach and wrap up. Ufuk, you're still muted.
Yeah, you're muted, Ufuk.
Okay, good. Now I'm not muted, hopefully. So I was trying to say, and I said a few times actually here, that the scope is relatively broad here, but we also go to a lot of review meetings, we see what we do and people's reaction, and we get questions, and it feels like it could have been even broader. But of course, we have to stay within our means here. So the last piece, I want to say a few words on the education and outreach because we actually put quite a bit of thoughts on that, and it is going relatively well. So obviously, the goal here is expanding and diversifying the U.S. workforce that can support what is coming up in advanced air mobility and the industry that's going to build around that. And the three main components we have been working on since the very beginning is a partnership with Morgan State University. This is mainly through Purdue. They have joint programs, and students can start at Morgan State, go to Purdue, finish there, or do some of their studies there. And that connection actually gives rise to nice internship opportunities as well. The second one is various high school outreach programs. Each of the participating institutions are contributing to. One I'm going to highlight that is close to me. One of my students here is teaching a local high school. This is Del Valley Independent School District and their technical education program. And my students developed a few short courses. They periodically go and teach and try to attract students to additional conversations and to STEM areas. And Karen Wilcox has been leading a workshop series over the years to attract candidates from underrepresented genders into aerospace engineering, and we are slowly actually tailoring that workshop series toward the advanced air mobility type discussions. So this we had planned and it is going relatively well. And one other thing I want to highlight is probably pretty unique for 2 ULI projects. This is a program that we had last summer between 2 ULI projects. The one that is led by Stanford and University of New Mexico. Miko Oishi is our collaborator on this effort. We recruited undergrad students from University of New Mexico and Hampton University, 2 of the participants of the other ULI project, and they visited University of Texas and had a 2-week research and training program that we had here, which included research time with grad students, but also visits to local industry and other professional development activities like how to do research given by the librarians and how to write a CV. And that would hopefully be useful for them in the next steps of their careers, which some of them are going to hopefully choose to stay in STEM areas. So that's it. Reminding that this was autonomous aerial cargo operations at scale, and with all these partnering institutions, we will stop here. And if there are any questions, we'll be more than happy to take.
Thanks, Dr. Kapia. We only have about 6 minutes, so I'm going to get into the questions in the chat. The first question in the chat was asking JP to clarify what they meant by dynamic certification, dynamic insert system component versus others. And then he also asked Ufuk, how do you guarantee that all assumptions are valid simultaneously in your synthesis satisfy the requirements?
Yeah, I saw those 2 questions from Eddie, and I think both of them are geared towards Ufuk. So I'll defer to Ufuk.
Yeah. What I mean by dynamic certification is when we use the word certification, it has been and maybe still is that we certify a system for a use case once, and then once it's certified, we deploy it, right? And with all the dynamic operation environment that we have with lots of participants at different levels of training and capabilities, as well as including functionality that, for example, rely on learning type algorithms, it will be relatively impossible to have one-off certification of a system to operate for the rest of their lifetime. We feel like the certification needs to be actually spread over the lifetime of these systems, and we need to reinterpret it as not just one-off signing, hey, you can deploy the system, but it should be an iterative process of risk management, understanding the risks that we may have with deploying of a system, and then as we interact with that, hopefully with the refined understanding of it, reduce the risks, and at the same time expand the use cases and the context in which we can continue to deploy the system. So that way of rethinking about certification, I just refer to as dynamic certification.
Thanks.
And then the assumptions question, I'll take that question offline. It is relatively unclear or not straightforward to actually indeed, if you are making a bunch of assumptions, whether these things actually are valid as you deploy the system. Whoever asked that question, let's discuss it offline.
Thanks. There's another question kind of, I guess, going on to asking if you assume vertiports would be privately owned or public. They say it's a factor that would impact.
Yeah, I'm typing an answer, right? I'm almost done typing the answer, but I'm happy to answer it. So far, we've been focused on understanding what we would do to serve the demand without considering the economic piece. When we were doing the congestion management, even though it was in the airspace context, that was the idea there was to actually see how it would translate to private people, private entities wanting to do the congestion management. So I think our broad assumption would be that vertiports will be privately owned, largely. Or at least we want to know what would it take in order for to have a viable vertiport business, right? Like economically viable, sustainable vertiport business.
Thanks. The next question in the chat says, speaking of parametric sensitivity analysis in TC1, are you assuming operation-wise? I'm not sure what that says. It just says, are you assuming operation-wise? If so, what parameters of the operation are you looking into in the sensitivity analysis, and do you consider regulations of the FAA in defining states in the Markov decision process?
Stephen, which question did you read? I got distracted.
It is Yona's question, the most recent at the bottom.
Speaking of parametric sensitivity analysis in DC1, are you assuming operation-wise? If so, what parameters of the operation are you looking into? That is a relatively abstract piece of work, but you could, for example, take as an example, in different environments, in urban and rural environments, what is the likelihood of communication delay or loss of communication when a system is to interact with someone else? That's just one example. You can think it as the parameters as those things that affect the transition behavior of the system, but are not directly controlled. Communication could be one, weather conditions could be another one. So those indirect effects on that can alter the transition behavior of the underlying system.
Thanks. And I did give April Lynott in the chat, who said they would like to talk to you a little bit more about the outreach work that you did. I gave her your email. And speaking of email, is there an email or a website that people can go to if they would like to follow up with extra questions or follow the work that your group is doing as you finish out your ULI in the next year or two?
I will take the responsibility of routing people to the right places. I just put my email address in the chat.
All right, thanks. So once again, I wanted to thank everybody for taking the time from the speaker side to brief everybody on the work that your ULI team is doing, and then thank the audience for attending another ULI Tech Talk. You can see we have an email in the chat if you would like to follow up with any questions, and this video will be posted on our website sometime in the near future. So thanks again to both sides for taking the time out of your day for another ULI Tech Talk, and have a good week.
Thank you.